Okay, so today we're going to be talking about color systems, and we've already talked about color, like the colorants, right? So that was in the chemical evidence side, where we got into the chemistry of what makes the colors. Today we're on the physical properties side. So we're in the physical properties part of the course, and so color itself is a physical property. It's not a chemical property. Although chemicals create the color, we're going to be talking about physical classification of color. So does this part have the same color as that part, or this piece of evidence versus this suspected article of clothing, or whatever. We're trying to match colors here, and so this is part of the physical comparison of evidence, where we would say, is this color the same as that color? Well, you can't really depend upon our descriptions of color. This are objective descriptions of color. So, color is perceived. When we look at it, it's perceived. But if I tell you, well, it was a color, it was puce. What the heck is that? I don't even know what puce looks like, but I know that it's a color. I've heard that. Okay. But I have no idea what that word means. And so this always bothered me. When I was at Pantex, I was at a plant that made explosives. It was an explosive production facility. And they had an acceptance criteria. What an acceptance criteria is, if we receive a shipment of explosives from a manufacturer, in order to receive that particular explosive, it had to have the color of burnished gold. It could not be green at all. Okay? I don't know what burnished gold is. And I thought to use these names for colors was a problem, because names of colors are just, I mean, go to the paint aisle and look at all the names. Dusty sunset. Is it blue? Is it gray? Is it orange? A sunset could be orange. It could be red. What is a dusky sunset? Or, you know, so I like to think of color as a quantitative property. So we want to talk about, again, this is the RGB lab revisited that you did in PChem 1. So we'll go through the quantitative colors coordinate systems and look at those, because those are the best way to compare two objects, is numerically. And then we'll talk a little bit at the end about the different colorants, inks, toners, and paints, and focus on their physical properties. So color perception is a learned behavior. We learn our colors early, okay? And I didn't do this because I didn't want to harm my children, but I thought, colors are just made up. We teach our children the colors. What if I taught my daughter that red was actually green and green was actually yellow, and yellow, you could do that, right? If you had an isolated child, you're some like mad man homeschooler, and you just give things different names, there's no way to correct that, because it's not numerical, right? If I tried to tell them that 5 was 6, that's a little harder to do than say that blue is actually called dust or something like that. Okay, but I didn't do that, thank goodness. But it's purely artificial, but it's agreed upon. So we agree on the names of these colors, because as soon as that kid got to kindergarten, they'd be like, no, that's not blue, that's yellow, and they'd get in a big fight. Okay, kind of like a wedding colors or something like that, or kitchen paint. But then there's this sort of effort in the printing and in the textiles industry and in cosmetics to come up with some standard colors. And so this is where the Pantone color system came in, 1962, pretty early. Pantone was founded as a manufacturer of color cards for cosmetics companies. And so they came up with these Pantone color chips, and you have a Pantone color guide, which this is made out of plastic, and you can fan it out and kind of find the color that you want. And then these are standardized colors. So this is a way to standardize the color, is the company Pantone put this out. And then they also made the color chips. So they're standard plastic chips of little, when I say chips, it's like a little plastic sample that's about an inch square. And I bought one of those at Pantex because, again, I wanted to, like, what is burnished gold? Can we give it a Pantone color? It's like Pantone, this one right here, Pantone 203M. So I could say only accept this explosive if it's Pantone 203M, or maybe no darker than 205 and no lighter than 201. So they could have those two chips, and they could go over to the loading dock and they could look at it and go, yeah, that color's between these two. We're good. Get the get the forklift and deliver that explosive. Because at that point at the receiving dock, you can reject it. And so if they can do this color thing, burnished gold was their acceptance criterion, and they had to be trained on what that was. So the receiver would look at it and go, not the right color. We're going to reject that shipment. Okay, so we could use Pantone standard color chips to do that. You could do that with, again, it was a cosmetic company. But once they had made this effort to standardize the color, then it became used in printing and all of these other areas. They started using the Pantone color chips. And you'll still see on some, like Sam Houston State has branding guidelines. If you go onto Google and type in SHSU branding guidelines, you'll get a little page that our marketing people put out. And they'll tell you what the color orange is, what the color blue is, and all these accent colors that we have. We have some really weird accent colors. You can go check it out. It's strange. But it'll have the CMYK values. It'll have the RGB values. It might even have, I haven't checked, might even have the Pantone values. So when you see that, now you know what that is. Okay, so then there's also quantified color where we put some numbers to it. And this is the CIE, which is French for Commission Internationale. I don't speak French. D'éclairage, I'm sure, I don't know. But it's color. So Commission International for Color, CIE. And so it standardized all three parts for color perception, because the color will change if you're in a dark environment or a lighter environment and so on. So the standard illumination is a piece of it. The observer is standard. So the angle or of observation angle, how much you're seeing, whether it includes just the macula or the rest of the retina, then you will get a little bit of a different color feel if it's like you have a narrow field of view or a wider field of view. And then also the standard sample and observation geometry. So, and it gives us numerical data. So I really appreciate this. It's a standard source profile, which we'll see the pigment functions, and we'll see the standard color spaces. Now, in order to prepare all of the different slides on this, I've used these 5 cuvettes. This has water in it. This has got potassium permanganate. The blue is copper sulfate. The green is nickel chloride, and the red is methyl red, an organic like pH indicator. So those are just some solutions that I prepared in my office and took a picture. This was a long time ago. I took a picture with a little $30 webcam and got that picture of those different samples. So these are the standard illuminants. And so let me show you a couple of these. So this one, this A is like a, I would say, incandescent bulbs. And it's orange. Have you seen those? I mean, it's been so long since that's been very common, but like an incandescent bulb is a bulb with a filament in it. And it gives off a kind of a yellowish light, yellow-orange light. And does that make sense? Look at this illuminant profile. Yeah, it's giving you lots of red light, right? So this is the intensity in the red region. This is the intensity in the blue and violet region. So here's blue, indigo, and violet. Roy G. Biv in reverse here. So red is over here in the 700s. Blue is, indigo and violet are down in the 400s. So it's not very much blue, a lot of red. So that's an incandescent bulb, probably 4,000 Kelvin. If you look at the color temperature at Home Depot, you go to buy light bulbs, they got a nice little display, and you can look at the different light bulbs, and they'll have the 4,000 one, and it's kind of red looking or orange looking, and then you get into the 50,000 D50. That's this one right here. That's 5,000 Kelvin. And notice its maximum, it's a very broad maximum, but its maximum is right about here. And then you have the 65 Kelvin, 65 right here, which is 6,500 Kelvin. So its maximum is a little bit more to the blue. So notice this A illuminant is going to be maximum down here. So that's from PChem 1. It's like the first week of lecture. We talked about the black body radiation curve and Wien's law. And these maxima are following Wien's law. And this is the Planck distribution, a black body radiation curve. And it's a function of temperature. The higher the temperature, the more blue it's shifted. The lower the temperature, the more red it's shifted. So these color temperatures are given to kind of match a black body radiator at that temperature. And the color of what you see reflected off of a colored object is going to depend upon how many photons of light you have in that range. So illuminant A will make objects look a little bit more red, and illuminant D65 will make things look a lot more blue. And so it matters. So if you're taking an evidence photo and you've got a flash that's going to produce, say, a 6500 Kelvin photograph, a flash that's going to put that kind of light on the object, and then let's say you print those off and then you give it to somebody and they're in a room, and the room lights are like soft white lights imitating a 4000 Kelvin light source, they're going to look at that image and it's going to look a little different, okay, than the forensic photo. So this is the physical properties of the substance that we're taking photographs of. The printing out on printers, showing on a projector, showing on a computer monitor. It's crazy complicated because we have different color profiles for what we print out, a different color profile for the monitor, a very different color profile for the projector. So what you may see on your computer screen may not present well through a projector, and the jury is not going to be looking at your computer screen. They're going to be looking at the projected image. So color management is really where we are in all of this. And I don't know that they've attempted to solve that problem. I don't know if it is completely solved, but when you look at your computer monitor and the projectors and so on, color profiles is what you're looking for, color management profiles. And so for like perfect work, trying to manage that color, if you use color management profiles in your printer, on your computer monitor, and on your projector, they should reproduce the same color sensation in all of those. Okay. So this is just the source of light. These are just the different profiles of the sources of light. Okay, here's the observer. So this was done in 1931, a long time ago. Okay, and what they did was they put observers. They had a screen here that masked it and gave it a two degree opening, on the observer's eye, so that we're fully in the color sensitive macular portion of the retina. Okay, and then they had a partition, and they had an upper part. It was a white screen, so it reflected all wavelengths, and the upper part had these three RGB lights that were filtered, and this person, I'll draw their little hand up here. That's a hand. Okay. And there's a little knob for the blue. Look at that. It turned out okay. Okay. So you can replace this with a monochromator. So you've got a prism here, and you like pick a particular wavelength of light. And so let's say we pick, I don't know, like 385 nanometer light, and we're shining that down on the bottom. Okay, and so we got 385 nanometer light, and this person adjusts the knob on the blue and the green and the red lights until the top and the bottom look like the same color. Now, are they exactly the same color? Well, it's hard to say because we're getting three lights producing the top color, and we're getting only a single wavelength, plus or minus a little bit, on the bottom. And so it's like we're sending 385 nanometer light into the eye on the bottom half of that image, and then we're using knobs to reproduce that same sensation, because that's what this is. Color is a sensation in the eye. Create the same sensation as 385 nanometer light. And we adjust those knobs, and then they record where the knobs are set. In 1931, they had to do it manually. Now we would use a computer to adjust those. And so we can replace that bottom light with a monochromator to test. And what they're actually doing when adjusting those knobs is they're actually capturing the signal from each of the three pigments in the retina. Because there's a pigment sensitive to the blue, there's a pigment sensitive to the green, and a pigment sensitive to the red. So this is what we would see. They would adjust those three. So let's go here to let's pick this wavelength right here since they're all three. So they would adjust these three knobs, and they would get, you know, this value for the blue. Come on, pen. This value for the blue, this value for the red, and this value for the green at that particular wavelength. So this particular wavelength would produce a color sensation of purple, and then they would adjust these three knobs until they got the same purple. And then they would move the monochromator a little bit over here, and when we're at this wavelength, the blue would be totally zeroed out because it's at 0, but then the red would have come up and the green would have been sort of at its maximum. And then they move the monochromator over here, and now green has come down a little bit, red is at its maximum, blue is completely zeroed out. And so they're mapping out the absorption spectrum of the pigments in the eye using these three knobs. It's really kind of crazy if you think about it. The brain is the analyzer, and it's causing this signal for these three pigments to go up or down. And so it was a way for them to map out the pigments in people's eyes. And they did this with many different people, and they realized, okay, these are the average signals that we get from the pigments in the eye. So that's why they're called the observer functions. These are the actual sort of spectra of the pigments in our eye. And I think it's a fascinating experiment. So this is a little bit more zoomed in with the colors in the background so you can kind of see where they are. Now, it's a little strange that the pigment, the red pigment, actually has a little bit of a blue absorption to it as well. So when we were down here at this wavelength, green was really low, and we would expect red to be 0 because we're way over in the blue, but red wasn't 0. Red came back up and it had this level of knob, and then the blue was really at a maximum. So we were able to map out some unexpected things with the red pigment. The blue behaves pretty expected, like you did. You have lots of blue down in this area, and it goes to 0 and stays 0. And the green starts at 0 and comes up around the green and the yellow, and then it comes back down. And then this is the D65, so the 65 Kelvin illuminant function. Any questions to this so far? This is all of the reflectance spectra of crepe paper. So I went to the party store and I bought blue and brown, green, orange, white, yellow, and so on. And we did reflectance spectra on all the different crepe papers. And then used the camera to kind of get a picture of them. And this is the color, the accurate color of what they looked like. You know, the brown is not like dark brown, it's kind of light brown, and green was kind of a pastel type green, orange, white, and yellow. And these are the reflectance spectra that you see. So this is the light being reflected off of the surface. Now, you've heard of red and, or you've heard of blue and yellow make green, right? And so if you got the green paper, what's happening? You would say, well, the green paper, you know, if I had yellow in that pigment, it should reflect a lot of this light. So how do I get green out of it? What happens to this light? Well, if I've got the yellow pigment in that paper, it should reflect the yellow, but the blue absorbs the yellow. So the blue drags that down to 0. So the light that bounces off the yellow pigment gets canceled out by the blue pigment and pulled down to 0. And the blue reflects blue light. And so you would expect the paper to be blue because the pigment's reflecting the blue, but the yellow pigment drags that down to 0. And so they're interacting with each other. The one where yellow and blue don't drag it down to 0 is right in the green region. And so yellow and blue do make green. This green is preferentially reflected here in this region where the yellow and the blue don't absorb as much. And so by subtracting the blue subtracts the yellow subtracts the blue, and what's left is green. And so that's why yellow and blue make green. Now that's subtractive color. The pigments are subtracting color out of the spectrum. Now color is observed, not absorbed. So we were just talking about the blue and the yellow sucking light out of the phenomenon or the reflection. And so what we have, if we have a blue cuvette of our liquid in a cuvette that's blue, and all the white light hits it, the only light that gets through is the blue. So the red is absorbed, the green is absorbed, and so the blue light is transmitted. You've got all of your equations from analytical chemistry. The amount of light over the amount of light that hits it is the transmittance, and that's e to the minus a absorption value. You take the log of transmittance, you get the absorption. Now we've got two types of reflectance. We have diffuse reflectance, and the best way to measure diffuse reflectance is with an integrating sphere. Oh, I've got it written right there. Yeah. So this integrating sphere takes the reflectance at all different angles, and they bounce all around and end up coming out this side slit. So it's got a hole in the side, and all the angles that the light comes off bounce around in there until they make it out the side. So it's 90 degrees to the incoming light, and so no incoming light is going to just take one bounce and come right out. It's going to be all these other bounces and they come out. Now, how do we get the inside of this to be so reflective? We typically will coat the inside with a white substance like barium sulfate. So they'll make a barium sulfate slurry and they'll mix it with a little bit of glue and they'll roll it around inside this sphere so the inside of the sphere is white. We have one of these in the lab, but the little source burned out. It had its own source and the source burned out. But it was really neat when it was working because you could look in the side and you could set it on a colored object. So when you have it on a white object, you see the white inside of the integrating sphere, but then you move it to an orange object and the whole inside of that sphere turns orange because all of the light's bouncing around in the sphere and it's coming out and hitting your eye. So in this case, if you're looking in this side port, you're giving red, green, yellow, all the different wavelengths of light hitting this substance, but then if you were to look at it right now in this situation, the whole inside of that sphere would be blue. So the sample absorbed all of the other lights. Now, whenever we're doing the reflectance measurement, we always do a black and a white. So we have the baseline, white minus black, and then we take this IS minus the black. And so that would be our ratio, our reflectance ratio. Then there's specular reflectance, and this preserves the reflecting angle. So you draw a normal to the surface, and this angle matches this angle. That's the criterion for specular reflectance. So this angle of incidence is preserved in specular reflectance. And there you're really looking at the source. If this surface is really smooth, you see actual image of the source. If the surface is rough, you just see the color of the source. And so you don't always get the blue, even though the sample is blue, because this incident angle is preserved, you get a lot of the wavelengths of the source and you learn less about the color of the substance. Total reflectance is the sum of both of these. Okay. So we have that Ocean Optics visible spectrometer that you used in PChem 1. It's easy to calibrate, tiny little spot size. It is field portable, so if you did have, maybe in the future, a reason to go to a crime scene and actually measure the color there, you could have these things be portable. These visible spectrometers now are miniaturized and USB compatible. Like you can just plug it into your computer and you have the source and the detector right there. The nice thing about them too is they're robust because it's using a diode array and a fixed grating, and so there's no moving parts. So it can be locked down and you can drop it, it's not going to break. And so this is what we have. We have the source here. goes to a fiber optic. You do the dark reference, the white reference, and then the colored object. And notice how we're hitting this, the specular reflectance angle is going straight down. And so if any light comes back at this crazy angle, that's diffuse reflectance. And so we would definitely get the color of that object going through the detector fiber optic into the spectrometer. Again, we do dark, white, and then the colored object. And we could easily measure the color of substances. And that's what we have in our lab. Here's a ocean optics paint analysis setup. It's very, very similar to what we have in the lab. We have a halogen lamp source. We have an attenuator that can cut the light back to where it doesn't saturate the detector. So that's a needed feature. We have the sample, we have the spectrometer, and then we have the white and black reference standards. So barium sulfate is typically the white standard. Black, probably carbon black, printer toner and such. Now, basic color analysis, you might have learned this in freshman chemistry, which is the color wheel. If a spectrum absorbs in the yellow, it'll give a violet spectrum, but this is, limited. What if there's two peaks, etc.? So this is a better color analysis. This is the way we quantify color. So if you have these samples here, you run them into your visible spectrometer, and they produce this spectrum. So this is the potassium permanganate spectrum up here. And this is purple. So what makes purple? Well, red and blue. You can see up there it's transmittance. So the red light is transmitted and the blue light is transmitted. You mix those in your eye and you perceive that to be purple. And then we take that spectrum and we determine the Tristimulus values, the capital X, Y, and Z. Now this is one of the few times when our variables are case sensitive. Okay, so you want to make sure that capital X, capital Y, and capital Z, you understand those are the Tristimulus values. They're roughly, X is roughly red, Y is roughly green, and Z is roughly the blue. Okay, and then we can transform those X, Y, Z values to RGB values. And then we can convert those RGB values, which range roughly from 0 to 1. If they go above 1, you just cut it back to 1. If they're less than 0, like a slightly negative, you bring it up to 0. And convert those to 8-bit values. You just multiply that by 255 and cap it at 255 and take away any negative values. So this is the range that your computer is looking for in terms of an 8-bit value. And then you can draw a color square and you can go into color and edit it and make it those RGB values. And this is the full loop all in one figure. So we start with a colored substance. We take a transmission spectrum of it. We run it through the math, which we're about to talk about, to make the Tristimulus value, convert it to RGB values, and then we can use that on a computer to display that color accurately. And it matches well. So this came from a photograph, and this came from our standard analysis. Okay. Now, which is going to be more reliable? This is where we get into the forensics question. So this color or that color, which of these would be more reliable? We have two choices, the photograph or the standard RGB value. Y'all like the word standard? Yeah. What's standard about the standard RGB value? It's quantified, that's good. But I could certainly, in ImageJ, like circle a spot in there and get the RGB values from my image. But let's try to unpack what makes us more confident in the standard RGB values than the photograph. But I could have just gone in here and selected those and given you similar, like 3 numbers. Yes. True. But I mean, these cameras are pretty complex. Yeah. But focus on that word standard. Every step in this process is standardized. From the geometry in the spectrometer, the light source, the detector, the computerized analysis of the numbers. So this has got a standardized path to these numbers. Whereas my camera, I don't know what light source I have. Maybe I have a flash, maybe I have, maybe I don't. There's ISO values on my camera. There's all kinds of things that we would try to standardize, but this is more standardized. Yeah, question. Yeah, repeatable. And because it has that standard procedure, it's very repeatable. So if you could get, again, if it's a liquid sample, no problem, right? We can take that liquid sample through our spectrometer and so on. If it's a reflectance, like a solid object, you have to get a reflectance spectrum. You're going to have to do your best to do this, and that is standardize the geometry, standardize the source, standardize the detector, and all of that, and try to go through the same standard collection procedure so that you get a really repeatable color measurement. And then you would have these sRGB values for that piece of evidence. So that'd be the gold standard if you could get it. Maybe you only have a camera to work with, but this would be best. And then you could compare those. So, of course, in chemistry and my research and so on, we would use like Gaussian to try to come up with these colors too. But I don't think Gaussian would ever make muster in a courtroom. You know, like, you did what? Try to explain that to a jury. Okay. So this is standardized. The standard E308 is an ASTM standard that talks about all of these pieces here. And so any spectrum can be fitted with those functions. And so this is the standard procedure that we're going to go through. We're trying to sort of fit these observer functions to our spectrum that we get in our spectrometer. And we have those three pigments. Now, if you go to Home Depot and you give them a swatch of paint, like I want to match this, these are my countertops or something, I want to match this with the room paint, they have way more than three pigments. They've got, a whole carousel of different pigments, and the computer can say what squirts of pigments and how much will go in to reproduce this color. And the computer probably does something like make 50 different recipes, and which one has the best fit value, R squared, or some sort of hit quality function that says this reproduces that color the best, so use this recipe. And so then they say, okay, we need 1/10 of an ounce of red and maybe 1 ounce of blue, and they squirt all of those pigments into the base color and then shake it up. And then they always, like, I'm amazed, they'll like put a little drop on the color card and you're like, wow, it's the same color. It's amazing. So they're doing the same thing on the computer over at Home Depot or Lowe's or wherever you buy your paint. So this is the procedure. We take that visible spectrum and we match these different color observer functions to it using these functions. So I've color coded this. The S sub L, this right here, this piece right here is that illuminant function. So notice it depends upon the illumination. We would get different X, Y, Z values if we had a tungsten filament lamp, an A source. This is a D65 source. We have our actual spectrum of our sample right here. And these are all functions of wavelength. And so we would do this in Excel, where we could multiply every one of those responses at every wavelength and add them together. And then we have XL. This is the X pigment here, the red one. So, so at every wavelength we have this number times this number times this number added to the next three numbers times each other, added to the next. So we sum all of those up. And then we normalize them. I don't exactly know why we normalize it with the green, but we normalize every one of these with the green, the source times the green. So, and then for the Y value, we have the green one up here. And then for the Z value, we have the blue one. So our XYZ is similar to RGB. It's just not exactly the same as our computer RGB, but it's still roughly red, green, and blue. And so in Excel, we could do this with the sum product function. So this is saying at wavelength 1, multiply all three of these and add it to wavelength 2, multiply by each other, and add it to wavelength 3, multiply by each other. Okay. And that will give us our values. So this Tristimulus values started in 1931. And so that was a long time ago. And then as the computer age took over, we had now printers, we had projectors, we had even, computer monitors and so on. And so Adobe, Apple, and other companies that were dealing with these color producing objects, printers and projectors and monitors, they produced a worldwide standard for color management. So that's what I was talking about, the color management profiles. And they standardized this conversion of XYZ values to RGB values. So they made this matrix. So all of these companies, Microsoft and Apple and Adobe and so on, they agreed that these are the numbers they're going to use to convert XYZ values over to RGB values. So this is in your homework just to give you one more trial on matrix multiplication before you head out the door as graduating seniors. So there's a couple of these in your homework, and so it just reinforces matrix multiplication one last time, and it's left multiplied. So this is coming at our XYZ values from the left, okay? And so it's the top row times this column. So this number times X, this number times Y, this number times Z, all added together will give you the R value. Okay, and then the middle one, the middle row, times XYZ added together will give you the G value. And then the bottom row times the first column, the XYZ added together will give you the B. So that's how you do it. People will get the wrong answer because they'll do it backwards. They'll have let's see, I don't know if you can do it backwards, but anyway, somehow they'll do it backwards. But this is the way you do it. It's left multiply. Okay. All right. And so now the color may be accurately displayed on computer monitors and printers because we can generate the standard RGB values from the XYZ values. Now this is a three-dimensional plot, XYZ or RGB. If we want to plot it on a two-dimensional plot, we come up with the chromaticity coordinates. And so these are lowercase. So this is case sensitive. So this is lowercase. So pay attention in the homework when talking about little x and little y. This is how those are calculated. So it's capital X over the sum of all three is little x, and capital Y over the sum of all three is little y. And we don't use little z, but you could calculate it if you want. And so this is the chromaticity diagram. And so here's the x value, and here's the y value. And here's all the colors in this color gamut, and you even have the wavelengths of light kind of put around the outside. So down here, this is 400 right here. This looks like 500 right here. Let's see. 570. Here's 600. So there's a huge change in color from 500, which is really green. 550 is yellow. Let's see, is this 550? Yeah, 550 is yellow. 570, 580, 580 is orange. So there's a huge color change in the 500s. It goes from green all the way over to red at 600, and then way out here is 700. And then the purple colors are just kind of a mixture of light from 700 and light from 400. So this is a sort of a combo. There's no wavelength that's purple. The purple is between the red and the blue. So you actually have to have two peaks to get purple. You have to have some red light and some blue light to get purple. If it's subtractive, you need to subtract all of the green and everything in the middle so that the red and the blue are reflected. And so you can get purple that way. Now these dots here are the chromaticity coordinates of the different vials. And so this one is right here. That's the permanganate color. The methyl red, see, is a more of a pure red color. The green is way over here. That's the only one that doesn't really look like the image. See, here's the green here, but this looks more like a yellow green. And then the light blue is over here. And it's blue, but notice it's towards the white point. So this middle piece is the white point, and that's this one here. And so if you get away from the white point, it gets darker blue. If you get closer to the white point, it becomes like a pastel or light blue. So that's the chromaticity diagram. Also a great way to display color in 2 dimensions, and you can find some really nice ones. Okay. So this is how we do it in Excel. You first get the spectrum. We want to clean all of that up and just match the spacing in ASTM 308 is every 5 nanometers. So you don't need a high resolution spectrometer. So that's nice. You can use a cheaper spectrometer. So we de-resolve the spectrum and collect only the every 5 nanometers. We compare that to the X, Y, and Z values. You can download these from CIE. And then we can use that transformation matrix. You can type that into Excel. Again, that's left multiplication. And so here's what we have in that RGB lab. We get the sum product values. You can see those sum product Excel functions that we talked about earlier in the notes. We could take those values and calculate the X and Y for the chromaticity coordinates. And then we could use that left multiplication of that matrix to produce the sRGB values. Now notice they're all less than 1. There might be some that go a little bit above 1, but we're going to truncate those at 1. Or we can wait till we get to the RGB values and stop them at 255. And so when we talk about 8 bits in a binary system, you have 8 zeros all the way to 8 ones. You add that up, and it's 256, but it starts at 0. So it goes from 0 to 255. So this one is 255. This is 0. So that's our 8 bits. So when we talk about 8-bit color values, the maximum is 255. This is also sometimes called 24-bit encoding for color because there's 3 values, each of them being 8 bits. So we have 24 bits holding the color values. And so we clip the data. Sometimes these come out to be negative. So if this is negative, we would get a negative value for the 0 to 255. We'd have a negative number. So we're just going to stop that at 0. So in your homework, I think you calculate one of these and they come out negative. And so you don't, that's not the right answers. You're not going to use negative values. You're going to zero that out. If it's comes out to be 300, you're going to cap that at 255. You're not going to just convert it down to 255. You're just going to cap it. If it goes over 255, you just cap it at 255. That's the maximum that you can get. And then there's a bit for gamma correction for CRT monitors, but I haven't seen a CRT monitor in years. That's the big, deep ones, the cathode ray tubes, the old school TVs. So we don't need to worry about that. And then if you wanted to display this, so this is a tool that you may want to use. Let's say you were to determine the 8-bit color values of a piece of evidence and you want to display that color. Just about any program, whether it's PowerPoint or Excel or whatever, you can draw a square and then you can go in and edit the color of that square, and you can pick a couple of different versions of the color, but RGB is one of the options, and then you type in your RGB values and then it will color that square according to your standard RGB values. If you got your image and you wanted to extract the RGB values from the image, you can use a free program like ImageJ. You can download this if you just go and Google ImageJ. It's an image manipulation program written in Java. It was funded by the NIH for a biologist to analyze microscope images. And so since it was government funded, they put that up on a government website, and it's written in JavaScript so that other people can add plugins. So there's a lot of extra plugins written for this program. So it's a really good image analysis program. It's free to download and free to use. Our taxpayers paid for it, our tax dollars. And so here, like you see, I've selected a region in this image. Notice there's some dark regions and some light regions and so on. So if I were just doing you've seen maybe the little eyedropper color picker, it's picking a pixel. So which pixel do I choose? If I'm going in there, I'm trying to find the color of that object, I'm using the color picker, it's pixel to pixel, and I might get a dark pixel, I might get a light pixel. So that's not good. We want to use statistics and see how many pixels, what's the average or the most probable pixel in this image. So we can select that region and then go to analysis tools and pick the color histogram. When you hit the color histogram, you get this output, and you have this mode value, which would be the most probable. So the most probable color in that is 169, 0, and 30. So those are the RGB values, and those would be the, like I said, the most probable. So if this is a distribution of pixels for the red, the mode is going to be the most probable. And the green, again, it's going to come like that, this distribution. The mode for the green is going to be right there, and then right here. So the mode would be the most probable RGB values there. Okay. And then you can enter those into Excel too if you wanted to compare. So we did all right. We had an image here with the colors. We did the standard XYZ values, converted those to RGB values, made color swatches, and then we have it. So those top ones would be the standard colors for these 4 objects here. And so it's pretty good. Again, look at the different brightness values. So our camera looks a little dark there. If we brighten this level up, we can see, yes, that green is an option. So in the spectrometer, that green cuvette probably looked more like this, because the top values went through the spectrometer. Those were the colors that the spectrometer saw. Got my cheapo camera here. It looks like the green's a little too dark, but the spectrometer is going to be a more standard procedure. So I trust the spectrometer value more because everything's locked down. Now that's another thing too. So we've adjusted this image, dark and light. Maybe we brightened it up. You know, in terms of forensics, you need to document everything you do. And so we certainly have documentation for the E308 procedure, the ASTM procedure. We would document any manipulations we do for image analysis too. Now the reason the green wasn't as dark as the RGB color gamut can only display. Our computer is really kind of limited here. This triangle is all we can get out of our computer colors. Okay, so even though it looks like we're seeing more colors, the computer is displaying the green like right here, and the angle from this white point out, this green is the same color, even though you may convince yourself it's not. These rays out from the white point, hit this, that's the same color all the way out. How do I know? Because the computer can't display any other colors, and we're going through a computer right now. So the phosphors in our computer, the standard RGB values, they're only capable of giving us certain sensations. And this triangle contains all the sensations that we can get from a computer monitor. So that's called the color gamut. Printing will have a different color gamut, a different sensation profile. So this is the RGB color gamut that we get from like a computer screen or computer projector. There'll be a slightly different color gamut for CMYK for the printing. Here are the names. If we were to put names on all of these, and we have, you know, we go around with greenish blue and blue green and bluish green. I mean, I can't stand that, you know. Give me a chromaticity coordinate, give me a tristimulus value, give me an RGB, but we still try to, you know, was it blue? Well, no, it was more of a purplish blue. Are you sure? Or was that bluish purple? I don't know. It's hard to say. Then we have the LAB. So RGB, or here's another one, LAB, luminosity or lightness, chroma, and hue. And so this is, lightness is up and down. Then you have the chroma, which is sort of the red-green axis, and the hue is the blue and yellow axis. And you see this appear. And these are 3 different lightness levels. So here's lightness of 25. You see how dark all the colors are. And then we go up to a lightness of 50. And then we go up to a lightness of 75. You see we're getting more pastel. It's still a lot of, you know, more light if it's reflective, more light reflective. If it's transmissive, more light's transmitted. There's conversions from the standard XYZ values over to the LAB values. They're pretty complicated conversions. I was going to implement that in the PChem lab, the RGB lab, to get into LAB and Munsell color system. Woo, it was hard. Okay, I'm looking at the ASTM to convert that over, and I thought, it's losing me. I'm not going to try to get the students to do that. But if you ever do that and you write a software program or get it into Excel, because now you have those sweet skills in Excel, send that to me. So if you ever, after you graduate, say, DW, I did it. So I'll be happy and I'll give you all the credit. So then here's the Munsell color system. We talked about this on the last one. We had that nice NIJ coloremic test output that said, for marijuana in this situation with this test solution, it gives like an RB8 or something like that, a red, blue 8. And so we have all of these different colors around here and how far they are from the middle and how bright they are as well. So forensic photography, when you're taking photographs, what did we just learn? It depends on the illumination. It depends upon the angle and maybe the settings on the camera, how sensitive your sensor is. So it's best, if you're going to take pictures of evidence, certainly you want some placards to tell you, which piece of evidence it was. So you put numbers next to everything. You got a cigarette butt there. Put a little number there, take a picture so we know that that's evidence piece number 1. But if you wanted to get any color information out of that object, let's say there was lipstick on the cigarette butt, might be forensically relevant, right? If you're going to try to use that color, you better have a color card. Because a color card with standard colors will allow you to correct that image. So even if you were in crappy lighting, and so on, you take a picture of that evidence with the color card in view, and then you can adjust the whole image. You don't care about the lipstick at this point. You adjust the image until this blue is the blue that you expect. The yellow is the yellow you expect. The black is really black. The white is really white. And then you adjust that image so that the color card is accurate. Once the color card is accurate, then the lipstick will be accurate. And then you've not used the lipstick at all to cloud your judgment. You've just focused on the color card, and that allows you to accurately adjust your image for differences in lighting and so on. So that's how you would take your photograph and make it standardized. But I'm a big fan of not just the evidence marker, but putting this in the, if you could have one of these that had this on it, then you could have size measurement, color measurement, and then whatever documentation you want to have. I've used this term additive and subtractive color. Subtractive color is printouts. Your printer ink, if you have a printer like mine, I like the laser jets. I don't like the ink, you're always running out of ink. But man, are they pricey. It's ridiculous. But you're constantly running out of toner. You got to buy these things. And what do you buy? You buy the CMY. So cyan, magenta, and yellow. And then K is black. So CMYK, it's a four pigment thing, because if you look at it, that middle piece is supposed to be black, but it's not quite black enough, and so they add a black toner cartridge in there. One, if you're printing black and white, it just prints the black, but two, you can add a little bit of K in there to make it really black. Yeah. And I had a printer back in the day that if we ran out of black ink, it would say, do you want me to just like fake it by putting all the colors there? It was an expensive way to make black, but and it never quite looked black. It always looked a little blue. But anyway, so CMYK is better. And then here's the RGB. So our projector, this is actually what's happening in our projector. It's putting out 3 pigments, but we're getting all those different colors. And so when it's putting out white, you're getting all 3 colors from that pixel. And our eye is being tickled. All 3 pigments are being tickled at their max value, and so we interpret that as white. So it's really interesting. That's the additive color. Now let's talk about the colorants there's some terms related to the colorants. There's misconceptions that dyes or pigments are organic. Like some people have said pigments are inorganic and dyes are organic. And that may go back to the day when they were using like clays and things like that to be pigments and organics were dyes. But that's really not the truth anymore. The dyes and pigments can be both inorganic or organic substances. They can both be natural or synthetic. And so they're not interchangeable though. Dyes are soluble, so it's depending upon the carrier. So this substance could be a dye if it's in a carrier that dissolves it, but it could also be a pigment if it's in a different carrier. So you have some things that are soluble in organic solutions, so they would be a dye in an oil-based paint, but you could still use that same substance in an aqueous paint, a water-based paint, but in that case it'd be called a pigment. So it's really just how it's carried. It's carried to the surface in either an organic matrix or water matrix, and so it's about the solubility. The pigments are typically not just molecules. Let's say we have an oily substance, a hydrophobic substance. You're not going to get that to stay in water without a surfactant, and so you're going to have to put some things around that molecule, and it'll be suspended. So it'll be particles suspended in that carrier solvent. And so we could, of course, we have from the chemistry side, we have those azo, triarylamethines, and so on, and they could be acidic, cationic, anionic, and so on. They have typically they have some CAS numbers. We could if we could identify them, then we could get their CAS number. They also have a color index number. And so, like in this case, pigment red 48. That's kind of an unusual name. It has a color index number, 12,070. The calcium salt of that would be color index 48 -2 or .2, and the manganese salt would be 48.4. So all of that for red pigment 48. So you may end up getting into all of that for evidence purposes. Okay, of course, water is the most desired vehicle for environmental and health reasons, but we have other things like isophorone or glycol ethers or MEK, and then they add a lot. There's a lot of additives such as these surfactants. And so you might have a particle that's somewhat positively charged, surrounded by surfactants, which have those negative head groups, and then that produces a positive tail, and these can be stabilized in solution. And then you can also have fixing agents. Like you could have epoxides in there that react when the paint starts to dry and it produces an epoxy coating. This is really important in automotive because you want a very hard coat. You also have different kinds of evidence coming from different printings. So mechanical pressing, where it puts an indentation on the paper, you get that from typewriters or dot matrix printers. This again would be physical evidence. When you have a document, how was it printed? Was it like a Xerox machine? Was it a typewriter? Was it engraved? Okay, some of these mechanical pressings are still used for money because they're really hard to fake. Now, hard to fake for humans to look at it, but like reading dollar bills in a feeder, as long as it has the same kind of visible image, you can fake out some of the computers that are taking bills. And so a lot of people will pass counterfeit bills in cash machines and things where they're putting in dollar bills. So you go to, I'm not saying do this, but I'm saying like if you were at HEB trying to pass a fake 20 to one of the clerks, who's going to feel the paper and go, wait a minute, let me put this in my little UV light device and see if it has the fluorescent stripe or whatever, or if it feels funny, or they look at it and go, that looks like it came off an inkjet printer. We're not going to take it. But if you stick it in the machine, now I don't know, it'd be interesting to see if those machines were easily faked. Don't do this, but I'm saying it would be interesting to see. Maybe you could get them to, like if you're in the forensics students club, maybe y'all could print a bunch of 20s and talk to them and say, could we see if your machine could be faked out so that they know about it? That'd be a fun project to do, but definitely get the manager's approval. I don't want anybody to get in trouble. When we first got here, they caught somebody in Huntsville passing fake 20s around town. And they had taken an inkjet printer, a little HB inkjet printer. The Secret Service was here tracking it down. And I noticed, well, this is kind of a funny story. We were at Denny's, and the person was really scrutinizing the 20s that I gave her. And she's looking at the little UV box, and I was like, "What are you doing?" She's like, "Well, there's a fluorescent stripe," and so on. And our manager got mad at us because we weren't using the box to check for the fluorescent stripe, and we took a bunch of fake 20s. And I said, "Oh, really? They got you?" And she said, "Yes." And she said, "The Secret Service came, and they got the bills, and they're looking at them, and so on." And then about a week later, in the Huntsville item, we see the newspaper, and they had a picture of the printer that the student used to print. I don't know who it was. The the printer that the person used to print those 20s, and it was exactly the same printer that we had at the house. I was like, "Oh, wow, that's cool." So anyway, it was a cheapo printer. It was like $100 printer, and it was able to print convincing enough bills that it fooled a few people. Yeah, so that was kind of interesting. But if you felt the paper, you knew immediately that it was fake. And of course, a laser printer and copier, they don't press on the paper. They use static charge to get the toner to stick to the paper. So they'll take an image, they'll charge up this transfer cylinder. The toner sticks to that transfer cylinder wherever there's a static charge, and then the paper goes through, and the toner sticks to the paper. And then it's just a dust on that paper. Has anybody ever had a copier jam and you pull it out and the toner is still on the paper, but it's not been fused, and it gets all over you? So if after that toner sticks to the paper and makes the words and the image, it goes through a fuser that's really hot, and it kind of melts or fuses the toner to the paper. So without that last hot step on the way out, and that's why your copies feel hot, the toner doesn't stick to the paper. Okay. So it's blown on there with a static charge, or touched on there with a static charge, then it's fused onto the paper. Then you have thermal printers. Those use heat and paper to change the color of the paper. So there's something, I don't know how the paper works, but there's something in the paper that will turn dark if it's heated up. So there's like a little hot fingers that go down and touch that thermal paper and heat it up and cause a color change. So that's how thermal printers work. And then you have the inkjet, where you're spraying the ink on and letting the ink, this carrier solvent evaporate. Then we get into paints. There's physical properties about paints that you might need to know. Latex paint is now just become synonymous for water-based paint. Now latex, when we were talking about poppies and morphine, how it comes out of the milky latex of the poppy pod. Latex is sort of the generic term for sap, or the milky latex that comes out of seed pods. That may have been what latex paint was in the past, but it's not today. Today, it's all just engineered from scratch. They have water-soluble polymers and water-soluble paints and surfactant suspensions of pigments. And so then that's, dispersed. Here you've got this thick layer that you put down, and then the solvent, typically water, evaporates, and those binder agents polymerize the polymer and hold on to the color and produce a nice hard coat of paint on the surface. For automotive paint, it's much more complicated. You have the base metal, and trying to get some of these paints to stick to the metal is a trick. Okay, it has to be very polar to stick to that metal oxide surface. So you got a metal oxide, we got all these dipole moments on there. If you've got an oil-based paint, it's just going to sit across the top. It's not going to interact with those dipole moments, those oxides. Okay, so you need a primer coat that has got a polar part and a nonpolar part. So the primer coat will get in and will adhere to that oxide layer on the metal, and it'll have a property that lets the paint stick to that. Maybe you need a second primer to adjust those Hansen solubility parameters from the really polar piece to the really nonpolar piece, so that an oil-based layer will go across the top. Now that's for painting a metal surface. What if you have a plastic bumper? Okay, you have a different primer for the plastic bumper, one that's totally organic soluble, and will get it adjusted to the paint. So you adjust the plastic parts and the metal parts to the same intermolecular attractive piece, the same level of polarity, and then you spray your color coat on there, and maybe you have a hard top coat. But the bottom line is you can't just analyze the top part. You can't use an ATR on the top, because when you use an ATR, you're just getting the very thinnest layer of vibrational spectra, and you're not getting any of the color information. So it'd be best if you could take a microtome image, a cross section, and use ATR from the side. Or sometimes they'll get in and they'll buff the paint down to the metal, and so they'll take an angle, and notice you have now more of this layer because you're coming at it from an angle, and more of this layer, and so you can get a better spectrum. You could use an ATR, you could use reflectance spectroscopy, you could use Raman. There's lots of spectroscopic techniques coupled to microscopes where you could analyze auto paint. Then you can also look at the metal flakes, and then you could also characterize that clear coat. Clear coat is the easiest one to characterize because it's on the outside, but it probably has the least amount of forensics evidence. It's the color that you want to match, typically, in automotive paints. So 9:15, we did it. So that's all the physical evidence surrounding different colors.